This is my presentation on the physics of shark locomotion. An introduction to sharks. Sharks have been around for 450 million years. They are evolutionarily perfected for optimal water locomotion. We will talk about the physics of their morphology, mainly their body shape, their caudal fins, and their denticles on their skin. There are over 500 documented species divided into 8 orders. We will focus on the order Lamniformes and primarily the example of the short-fin mako. Key terms are biomimicry, the engineering of products, materials, etc. based on living organisms, dermal denticles, placoid teeth-like scales along shark skin, drag, a force that opposes an object moving through a fluid, viscous drag and pressure drag. Riblets are grooves in surface aligned with flow to reduce friction, and viscosity, a measure of a fluid's resistance to flow. Here's the basic anatomy of a shark. Lamniformes do not have the dorsal fin on the spine. All sharks have denticles, they all have caudal fins, they all have dorsal fins, pectoral fins, and an elongated snout. Here is the short fin mako, Isurus oxyrhynchus. Here is its taxonomy, and it is the fastest recorded shark in the world, reaching speeds of 70 kilometers per hour, and they are sadly endangered. So Lamniformes are tuniform swimmers, which means their caudal, peduncle, and caudal fin undulate. They have minimal head motion, but they have a very strong motion in their caudal fins. So because of this, they lack maneuverability, but they gain speed and stability. Here is a video clip of this in action with the short fin mako chasing a baited camera going 70 kilometers per hour. So the caudal fin is the primary locomotive organ for all sharks, but specifically the Lamniformes. And Lamniformes have a heterocercal tail, which means an asymmetrical tail, where the upper lobe is longer than the bottom lobe. And you can see in the x-rays here that the spine, the vertebra, reaches all the way to the tip of the upper lobe, giving the tail maximum strength and maneuverability. And we have the short fin mako starred in both photos. The heterocercal tail has 3 main functions. Lift. Sharks are negatively buoyant. They lack a swim bladder, and the tail provides upward force with a perpendicular jet force. They essentially have to swim constantly or they will sink. And you can see here the photo of the force of the tail perpendicular to the jet force. Maneuverability. The upward torque caused by the caudal fins will vary in trajectory based on the angle of the body. Force. Tail provides jet force, opposite in direction but equal in magnitude to the reaction forces. And this photo here on the right is of a bamboo shark, which is not in the order Lamniformes, but it's a really good diagram of what is happening. Because of the functions of the tail and the overall shape and morphology of sharks, they can do something really cool called breaching, where this is really impressive because of their mass, all the opposing forces acting on them, the water viscosity, and the initial starting depth of their ascent. This is really energy costly, and they do this for hunting, parasite removal, and potentially communication. We've all seen Shark Week, we've all seen air jaws. This is a great white shark breaching with a velocity of 11 meters per second, roughly, believe it's at 10 feet out of the water column, and it's starting at about 7 meters below. So that's a pretty impressive displacement. The optimal body shape is an airfoil. We can see this very narrow shape here. It's disrupting the water flow the least out of these 3 examples. And when you're in water, you have something called the viscous drag force, the force of friction caused by a flowing fluid. It is in the opposite direction to the movement. Viscosity of water is 50 times stronger than air, which is why we have viscous drag force. Airfoil shape minimizes viscous drag on the body. The pressure drag force forms when water is being displaced, causing pressure changes. The water rushes to low pressure, which causes friction on the body. The airfoil body reduces displacement, which minimizes pressure change, which minimizes the drag force. We see here how closely the shark matches the airfoil shape, and the airfoil shape has the lowest drag coefficient of 0.04, and this shape is the lowest, provides the lowest energy expenditure. So denticles are a part of the optimal body because they of how they move water over the shark's body. So here we see that the shark is accelerating forward and the water is flowing in the opposing direction, and when it hits the shark's body, it displaces. And this layer here is the laminar layer, and it's moving in one direction, it's not mixing, but as you get closer to the body, you start getting this turbulent boundary layer, which is high in energy consumption. There's lots of mixing fluid layers and constant directional shifts. So different shark species have different niches, and therefore they have different denticles. All sharks and rays and skates have dermal denticles. The main purpose of them is protection from predation, abrasion boundary if you're living in a rocky substrate, parasite barrier, and drag reduction. Denticles with riblets are found mostly in pelagic open water species. You can see here this pelagic shark has mostly drag reduction riblets, and the demersal nurse shark on the bottom has no drag reduction because it's not needed for their niche. So what do riblets do? Riblets disrupt the turbulent boundary layer, therefore conserving sharks' energy. As the chaotic water flows between the grooves, its vortex is disrupted and its velocity is reduced. This diminishes the drag force. The drag force is dependent on the object's shape, size, velocity, and fluid density. More riblets means more energy conservation, and more riblets means less drag force. So back to makos. The makos can do something called bristling, where the dermal denticles will lift about 50 degrees from the body, and they are lined with all of these grooves, riblets. So in this initial photo, the denticles are laying flat, and as the turbulent layer is moving, the grooves lift and trap the vortex in their grooves. And this reduces its velocity and allows the laminar layer to move over and not disrupting the shark's motion and reducing its drag. We can see here this short fin mako is sadly dead, and it has 16 different variations of denticle patterns with riblets, just showing how this species is optimal for underwater locomotion and why they are the fastest shark species ever recorded. So why do we care? Because we humans do something called biomimicry, where we mimic items in nature and engineer it in ways that are beneficial to us. So ways shark help us is in transportation. There's something called denticle paint. It's more of a stencil. This has been known to reduce friction of ships by 5%, and NASA uses riblets in aerodynamics to reduce drag and conserve fuel. In health and medicine, riblet surfaces are known to cause germ deflection. When combined with titanium dioxide nanoparticles, they can kill 95% of an E. coli culture in 1 hour. And in fashion, Speedo's LZR Racer swimsuit was worn at the 2008 Beijing Olympics, and 94% of the wins for swimming were credited to the swimsuit, and it was banned for technological doping. Thank you.